Hello everybody and welcome to Chapter 10 on polynomials. We finally hit the last week of our quarter and we're having the most fun. I swear this is the best chapter right here. This is one of my favorites because it really gets us ready for the basis of the algebra class. So what are we going to cover today? Well, we're going to go through a little vocabulary. Most of it we already know, but we need to make sure that we understand these terms. And then we're going to add and subtract polynomials. We're going to go through a few exponent laws. We're going to review the distributive law, and then we're going to work it in reverse. And then we're going to multiply some polynomials, and we're going to talk about scientific notation. Some of this might not exactly be in this order, as I'm going to shuffle in the distributive law a little bit early, and then return to it a little bit later to talk about the reverse. But those are the concepts that we are covering in Chapter 10 on polynomials. So going through our vocabulary, we need to make sure that we are aware of what we're talking about. Now, polynomials is a pretty big word. We need to be able to understand what that means. Now, poly wants a cracker? No, not that kind of poly. Poly means many or lots of them. And nomials comes from the Greek root word for numbers. But we want to be a little bit more specific as to what type of numbers are we really using here. And the type of numbers that we're really going to be using are terms. And so polynomials simply means that we're going to have many terms. Okay. Now, what's a term? We got to remember what that is. Remember, I said that is one of the key concepts that we need to leave this class with, is knowing what is a term. Okay? Now, a term is a number, a variable, or a product of numbers and variables separated by addition. Do I need to write all that down? Maybe I'll take a moment to do that. So once again, it's a number, a variable, or a product of a number and a variable or variables separated by addition. Now, if we don't understand the words in the definition, we're not going to understand the definition itself. So let's make sure we understand each part. A number, okay, we're good with that. A variable. Variable is just another way of saying a letter. Okay. A number or a letter or a product. Product, that's another weird one. Product means the answer to a multiplication. So we're going to be multiplying a number and variable, or variables, because you could put more than one variable together. And the terms are separated by addition. Notice the spelling of separated. The E's are separated by the A's, or you can say that there's a rat inside of it. Anything so that you start spelling it correctly. Separated by addition. Okay, so what are some examples of terms? Well, a number, 12, there's an example of a term. A letter, Z, that's another example of a term. A product of a letter and a number. How about 12Z? Haha. And then we can put these terms together. So I can put a few terms. I can say, okay, how about 12Z plus 14? Now I have two terms. 12Z is a term and 14 is a term. And the two of them are separated by the plus sign. That's how one term ends and the next term begins. Okay. Now, we also need to be aware that terms are separated by addition, but what happens if I have something like 3x squared minus 4x minus 1? I don't see any addition there. But remember, subtraction is the same thing as adding the opposite. So there's three terms there. The first term is the 3x squared. The second term is the negative 4x because the sign in front of the term goes with the term. Because remember, this is adding the opposite. Remember change, change? And so we have a negative 4x here. And the same thing for that last one. We do a change, so it's plus the opposite. And we have a negative one. So the three terms there are 3x squared, negative 4x, negative 1. Okay. Coefficient. That's just a big way of saying the number in front of the letter. Number in front of letter. So in that expression that we just did, the 3x squared minus 4x minus 1, the 3 is the coefficient on the x squared. The negative 4 is the coefficient on the x. Now, is negative 1 a coefficient? Well, there's no variable there. So they decided to have a new name for it. So instead of calling that a coefficient, we call that the constant. So the constant is the number with no letter. So that would be the negative 1 in that example up there. Okay. So the coefficient is the number in front of the letter. If the number doesn't have a letter, it's called a constant. Putting all of these terms together, a bunch of terms together, makes a polynomial. I call those choo-choo trains. The choo-choo train has to be attached by either a plus or a minus sign, and that's how they are coupled together to pull out of the station together. We have the standard form of a polynomial. The standard form of a polynomial is to put the highest exponent first. Highest exponent first. And then in decreasing order. Now the exponent is the exponent on the variable. Our numbers won't have exponents on them because we would simplify that and get rid of them. So notice on that problem that I put up there, let me rewrite it down here again. We had 3x squared minus 4x minus 1. I put the x squared term first, then the x, and then the constant is the caboose. The constant is the caboose. It's always the last one. Okay. So the highest exponent was the x squared, so that term went first, and then in decreasing order. What's the exponent on this x here? If there's nothing up there, the God of Mathland is always with us. He, she, it is sitting on our shoulder. Every number has an exponent. The exponent is a 1. We just don't see it because we're not going to write every single number with an exponent of 1 up there. I mean, literally, this 3 could have an exponent of 1 on it. The 4 could have an exponent of 1. The x has an exponent of 1. The 1 over here has an exponent of 1. We'd have all these little 1s hanging around. We don't need that. God needs to be with us, but not necessarily seen. So if there's no exponent up there, it's always a 1. We just don't see the God of Mathland sitting on our shoulder all the time. He, she, it likes to hide, but he, she, it is always there. Okay, so that's the standard form of a polynomial. You put your highest exponent first, and then in decreasing order. In this segment, we are going to be going through adding polynomials and subtracting polynomials. But in order to subtract the polynomials, we're going to have to review our distributive law. So we're going to throw that in there as well. But adding polynomials. Remember, polynomials are just many terms strung together. In order to add polynomials, we can only add like terms. We cannot add apples to bananas. We can only add bananas to bananas. So we need to make sure that we identify what are like terms. Now, like terms are terms that are alike. No, that's a terrible definition. We need something much better than that. All right, so what are terms again? Well, that's that number, variable, or product of a number and variable separated by addition. Oh my. Yep, keep repeating it until you remember it. So what makes those different terms like terms? And there's two criteria for like terms. Okay. The first criteria for like terms is that they have to have the same variable, or variables if we have more of one. Okay. So I cannot combine a term that has an x with a term that has a y because they're not like. They're not the same. But there's a second thing that you also have to look for. Not only do they have to have the same variables, but the variables have to have the same exponents. Now we talked about this in week 1 or 2 or something of that sort, and we've reviewed it several times throughout. So this is not anything new. We're just looking at it with the same variable, whereas earlier we looked at a's and b's as opposed to everything being an x. And now we're going to have things like x squared or x to the third power. Okay? All we need to do to add like terms, as it states up here, is to add the coefficients. Add the coefficients. If we're going to do all this work to make sure that we're only combining like terms, and like terms have to have the same variable and the same exponent, we will not change the variable or the exponent. We will not change variable or exponent. When adding like terms. And the same thing will happen for subtracting. So we're going to do all this work to combine like terms. We don't change the variable or the exponent. That is what makes them like. We only add or subtract the coefficients or the numbers in front of those. So here we have an example of this big, long, scary looking thing, which should not be so scary. What's happening here? Why are all those parentheses in there? I have to do what's inside parentheses first. Yes, but inside parentheses we have this polynomial. Those terms are not alike, so I cannot combine them. And then I'm adding another polynomial. So the reason for the parentheses in this chapter is to identify our polynomials. So I have one polynomial over here, I have another polynomial over here, and what's in between them is the operation that we are going to be performing. In this case, we are adding. So because I know my answer needs to be in standard form, which is the highest exponent first, what I do first is I scan all my exponents and look for the largest one. I see I have an x squared and an x squared. There's nothing higher than that. So x squared is my highest exponent, so that's going to be the first term. So now I go through and use different colors and use different ways. I underline them 2 times for the x squared, and here's a 2 times a line underneath it for the x squared. Those are the 2 like terms that are x squares. I have 7x squared and I'm adding 2x squareds. That gives me a total of 9x squared. Notice I did not change the variable or the exponent. Now I go to my next term. Because we started in the highest exponent, you just go in decreasing order from there. So the next thing I'm going to look for is an x. Here's an x. Here's an x. So I have 2x plus x. What is that going to give us? What's the number in front of this x? The coefficient is 2. What's the coefficient on the other x? Can't be 0 because what's 0 times x? 0. Then I wouldn't have an x there. What would make that x come back? Ah, God of Mathland once again shows its wonderful face. It's 1x. So we have 2x plus 1x, which makes a total of 3x. Now we need to separate that term from the 9x squared. How do we separate terms? By addition. It's still a positive, so we go plus 3x. Now we go to our next term. In decreasing order, well, since x doesn't go any smaller than that, we then look for the constant, that's our caboose, and I have an 8 over here, and what's over here? Oh, remember, the sign in front of the term goes with the term, so that's a negative 9. What do I get when I add a positive 8 and a negative 9? 8 take away 9 gives me a -1. You can write it as that, subtraction, or you could add a -1. But you need to separate that term from the previous term by either adding or subtracting. I cannot go any further as x squared is not the same thing as an x, which is not the same thing as a constant. So this is my answer, and that's okay. When I have a polynomial and I add another polynomial to it, my answer is going to be a polynomial, or several terms together, and that's okay. One of the things that we always feel is that we have to go down to a single number. Oh, I need an answer. No, we're not finding an answer. We're not solving anything. We're just simplifying stuff right now, gathering the like stuff together. As I said before, I think of this as a choo-choo train. And then each of the variables and the exponents represents a different train car. So here maybe x squared is the passenger car. And here I had the hopper car. And here's the constant caboose. Well, I had 7 orders of people in my passenger car, and I added 2 more. That gave me 9 that's still in the passenger car. So the name of the car didn't change when I added more to it. I had 2 loads in my hopper, and I added a load. Now I have 3 loads in my hopper. You don't put loads of people with junk that goes in the hopper car. The people get pissed off. So you can't travel together there. Okay? The same thing, you don't put the scrap metal that belongs in the hopper car in with the passengers. They don't return. They're not happy. Okay, so keep that in mind. And then the constant caboose, those don't go anywhere else. They just like to hang out at the end. Okay? So that is how we're going to add our polynomials. You simply add the coefficients of like terms. Now before we subtract like polynomials, or like terms of different polynomials, I want to make sure that we review the distributive law. It's going to help us remember the steps that we need to do in subtracting polynomials. So remember, the distributive law is stated something like this, that we have a number in front of parentheses, and inside the parentheses we don't have like terms. I can't add 3 to x since I don't know what x is. We can't just put a number in there. We don't know what it is. It could change. That's why it's called a variable. It can vary. But I do want to get rid of those parentheses. And so the other reason for parentheses is to indicate multiplication. So the 2 is being multiplied to that result. Well, we distribute the 2 by multiplying it to both terms inside to get our answer. So we would have 2 times x plus 2 times 3. And we'd simplify it. We don't really use the multiplication dot between a number and a letter because just mushing them together means multiplication. And 2 times 3 we know is 6. Once again, those 2 terms are not like, so we cannot combine them or go any further. Okay, well that's not so bad. Let's do another one. -4 times the quantity of x minus 6. Same idea, -4 gets distributed inside. -4 times x is a -4x. -4 times, remember the sign in front of the term goes with the term. So it's a -4 times a -6. Multiplying 2 of the same sign is a good thing. And so it's plus 24. Once again, those are 2 different terms. They're not like, so we cannot combine them. Well, that seems pretty easy. -3 times 5x, -15x, -3 times a -1 is a +3. Once again, the first term has an x and the second one does not, so those are not like terms. I cannot go any further, and that's okay. That seems really easy. All right, let's do one more just for kicks and giggles. How do I simplify that one? Uh-oh. Yeah, we can still do that. What's the number in front that's being distributed in? The god of Mathland, he, she, it, is always with us. So it's just a -1. Now what happens when I multiply a -1 to a 2x? A negative times a positive is a negative. negative 1 times this negative 7, negative times a negative is a positive 7. So the negative sign out in front is saying to take the opposite of what's inside your parentheses. So the 2x was positive, it becomes negative. The 7 was negative, it becomes positive. It just changes all of the signs inside. We're going to use that concept in order to subtract polynomials. To subtract polynomials, we need to remember that subtraction is the same thing as adding the opposite. We like to call that change. So you see in this example, we have 3x squared plus 5x minus 4. Once again, that's in parentheses, indicating that that's the first polynomial. We have a second polynomial in this parentheses over here, the negative 4x squared plus 11x minus 2. But this time we are subtracting. Now you need to remember that you are subtracting every term in this second polynomial. That gets a little bit confusing, and when we have negatives in here, then we have the tendency to forget that we're subtracting the negative. So we're going to do a different procedure, which is going to be a whole lot easier for us to remember. We're going to use, once again, that change, and the idea that we just went through about distributing through a negative. Because if you look at this problem and I take away or I cover up the first polynomial, the result that we have there is exactly like that last distributive property example. So we're going to do that same idea here as your first step. I'm going to do change. Okay? I like to say, okay, so the subtraction I'm changing to addition, and then the sign of the number right after I change. Well, the number right after is a 1, because remember, it's 1 that would be multiplied inside. That 1 is positive, so I'm going to change it to negative, and that's my second change. Remember, the first change is to go from subtraction to addition, and the second change is the sign on the number right after the subtraction. If it's positive, it goes negative. If it's negative, it goes positive. So now I see that I have a negative 1 times this quantity. According to our order of operations, we have to do the multiplication before we can add or subtract like terms. So my next step is to distribute through this negative sign all the way to every term inside the second polynomial. I did not do anything with the first polynomial, so I won't change any of that. That's still going to be 3x squared plus 5x minus 4. But now we distribute. Negative times a negative makes it a positive 4x squared. Negative times a positive makes it a negative 11x. And a negative times a negative makes it a positive 2. Make sure you are multiplying, don't start adding things. Now, because it's all addition of terms, we don't need the parentheses. So now we can go through and we can combine our like terms. So the highest exponent we look for first, that's a square. Here's a square, here's a square. 3x squared plus 4x squared is going to give us 7x squared. Then you look for your x terms. Here's a 5x, here's a negative 11x. Remember, the sign in front of the term goes with the term. That's why I underline it to go with it. 5 and a negative 11 ends up being a negative 6x. You can use that negative as a subtraction to separate your terms. And then you have your constant terms. So we have a negative 4 and a positive 2. One of each sign, we subtract and keep the sign of the larger. So we would go 4 minus 2, which is 2. The 4 is what we started with. It's negative. So our result is negative. Once again, I cannot combine a square with an x with a number that doesn't have a variable, so I'm all done. That is my new choo-choo train. Choo-choo. Here's another problem. Here I have 6x cubed minus 4x squared minus 3x, and I'm subtracting the polynomial of 8x squared plus 5x plus 2. I would pause it now and see if you can work this one through yourself. Okay, let's see how you did. First of all, I would do change. Now, I've done a lot of these changes through my time, and I've realized that I can even do a shortcut, which is even faster than what I did on that last problem. Last problem, I kind of showed all my distributive property, which is fine, and if you're at that stage, do it like that. Don't make yourself make silly mistakes because you're trying to rush your understanding. But I know that I'm going to change this, and then I move it inside, and I change all of the signs inside. So I'm just going to distribute that negative all in one. I'm going to make this negative, or the subtraction, into a positive, so I remember that I'm separating terms still. And then I go inside the parentheses after that subtraction, and I change all the signs. This is a positive 8x squared, so I make it negative. This is a positive 5x, so I make that negative. And a positive 2, so I make that negative. If any of those were subtraction, I would make them into addition. And now I've dealt with my change, and I can simply go through and combine my like terms. Once again, I look for my highest exponent first, and I notice that I have an x to the third. Oh, but I don't have any other x to the thirds. So that term, still part of my answer, but I don't have anything to combine it with. It's my highest exponent, so to be in the standard form, I put that term first. Now I go through and I look for my squares. Once again, the sign in front of it goes with it. So I have a negative 4x squared and a negative 8x squared, and we're adding, remember now? So when adding like terms, they're both negative, add them and keep the sign. So that would be minus 12x squared. Then we go for our x's, and we have a negative 3x and a negative 5x. Same idea here, they're both negative, so keep the sign and add the numbers together because we are adding. But then don't lose your constant. The caboose has got to come along. Well, there's no constant over here. Well, that's all right. It comes along just like the 6x cubed did, but don't lose the sign on it. It's a negative 2. So you can either put plus a negative, or I just call that subtracting 2, because adding a negative is the same thing as subtraction. And here is my polynomial result. So when subtracting, remember to change all of the signs in the second set of parentheses, or the parenthesis after the minus sign. Change the minus sign to plus, and change all the signs inside to the opposite of what they are. And then combine your like terms. So in the last segment, we reviewed the distributive law and reminded ourselves that when we had a number on the outside of parentheses, that we can still get rid of those parentheses by multiplying that number inside. Well, the distributive law is like all laws in math land. They go forward and they go backwards. What we just did with the distributive law is say that, hey, there's a number on the outside of these quantities, and then we take the a times the b and get ab. And then you take the a times the c and get ac. However, this can also work in reverse, in which if we have two terms that share a common factor, factor. Remember, factors are the stuff that gets multiplied together. So in the first term, a and b are factors. In the second term, a and c are factors. If they share a common factor, which is the a, you can pull that shared factor to the front. This is called factoring, or using our distributive law backwards. So one of the examples that we had, we ended up with the result of 2x plus 6. So we want to say what goes into, so kind of like when you're reducing your fractions, what goes into both terms. And we want the largest thing that goes into both of them. We say, well, 2x has the number 2, and that's even. 6 is even. So if you want to rewrite it, it's 2 times x plus, and 6 can be rewritten as 2 times 3, as they mean the same thing. And here you can see now that they both share a 2. So I'm going to pull that 2 to the front. You only write it once when it's in the front. And then you say, okay, if I pulled that out to the front, what am I left with? Well, I took the 2 out of here, so I'm left with the x. There's still the plus sign to separate our terms. I took the 2 out of here, so I'm left with 3. So now we wrote the polynomial, the terms, as a product. This is called factored form. When it's written as a product, because remember, factors mean that you're multiplying it. It's 2 times this quantity. This 2 times the quantity of x plus 3 is the same thing as 2x plus 6. It just looks different. Let's do another one. One of the other examples that we had on there was, our result was negative 4x plus 24. So what's the common factor? What goes into negative 4x and 24? Now technically we have 2 different answers to this, or potential answers to this. We have the 4 or we have the negative 4. Now I like to keep the term that has the variable positive, so I'm going to take the negative out with it. So I would pull out the negative 4 to the front and then say, what do I have left if I pull out or divide the negative 4x by the negative 4? And the x is what's left. What am I left with if I pull negative 4 out of 24? Well, think of the distributive property the other way if you need to. If I was multiplying this back in, what do I have to take negative 4 times to get a positive 24? Negative times a negative is a positive. And 4 times 6 is 24. Yes, you could have taken out the positive 4, and then you would have been left with negative x plus 6. That also would have worked. That's called taking out the common factor. Let's do a couple more. What if I had negative 15x plus 3? What's the greatest common factor? What's the thing that they both share? So essentially, if this was a fraction, what would you have reduced? If the negative 15x was on top and the 3 was on bottom, what would you have reduced to make that into a simplified fraction? It's kind of that same idea, but instead of getting rid of that number, we have to write it as part of our answer. So what goes into both negative 15x and 3 would be a negative 3. Once again, I'm pulling the negative out because I want the variable term, the term with the x, to be positive. So if I pull that out, what am I left with? Well, negative 15x divided by a negative 3 is a positive 5x. In the second term, I have a 3 and I pull a negative 3 out. What am I left with? It's not 0. We're not subtracting. It's not 3 minus 3. I'm dividing this 3 by a negative 3. Remember, once again, to multiply back in, I need this spot here. I need to represent this number. So negative 3 times what would give me a positive 3? We need that 1 as a placeholder. You can always check by distributing through to make sure that you have the right answer. Negative 3 times 5x is negative 15x. Negative 3 times a negative 1 is a positive 3. Now in that first example, I kind of wrote it out as different factors. Maybe that would be easier for you to see. If you look back into our original problem, negative 15x plus 3, I'm going to say, okay, I do see the 3 or -3, so I'm going to say -3 times 5 is still 15, and then times my x, and then I need, okay, plus, and I have this common of -3. Well, what do I take -3 times to get this +3? Would be a -1. Now maybe it'd be easier for you to see that both terms share a factor of -3, and that's what gets taken out in the front. And then you identify what do you have left over. In that first term, we took out that -3, so we have the 5x left. We took out the -3 here, so we have this -1x. You could do plus a -1x or just minus. Either way gets you that same answer. Factoring out, no, we just did 2 terms. You could have 3 terms and have the exact same thing. What number goes into all 3 terms? That's the number that gets pulled to the front, and then you see what do you have left over. When you're done, double check it to make sure that you have the right answer by multiplying the number back in. You should get your original problem. And that's using your distributive property in reverse, called factoring out the greatest common factor. So next on the docket is going through some of the exponent laws. Now there's about 7 exponent laws or so, depending on how you wish to word some of them. We're not going through all of them in this course. We're only going to be covering about 4 of them, just so you have an idea of what's going on. We need a couple of these. We need the first one in order to multiply polynomials, which we will be doing next. Then we're learning one so that we can apply it to a couple others. And we're learning those so that we can understand how to write numbers in scientific notation. But we're going to go through all of the exponent laws right now, and then use just a couple of them in the next segment and the others in the segment after. Okay. So, exponent laws. Well, we have laws everywhere in math land. And the exponent law here says if we are multiplying like base numbers, so b for base, and we have some exponents, so it's b to the m times b to the n, where m and n are whatever numbers you like, we can simplify that and write it as a single factor. So in multiplying like base numbers, what we do in that case is add the exponents. So the result of that is going to be b to the m plus n. Now, how does that work? Well, let's think of a couple examples that would match up with that. If I had x cubed times x squared, we know that x cubed really means, if we were to do this the long way, x cubed expanded really means x times x times x. And x squared means x times x. So how many x's are being multiplied together? 1, 2, 3, 4, 5, Well, instead of having to write it out like that every time, we notice that 3 plus 2 is 5. So after doing a boatload of these, instead of expanding it out like this, we can apply the law that when multiplying like base numbers, you add the exponents. And just to make sure that we're on the right page, what happens if that was 2 to the third times 2 squared? What's our result in that case? Same law applies. That is not a 2 times 2. Only 2 to the first times 2 to the first gives us the answer of 4. This is not 2 to the first times 2 to the first. It's 2 to the third times 2 squared. So you do not multiply the base numbers. Notice in the problem here, it's b to the m times b to the n, and the base stays b. It did not change to anything else. So the same thing goes here. We are multiplying like base numbers. Big number is the base number, that's the 2, so the base number does not change. We simply add the exponents 3 plus 2 to get 5. And in this case, you would then expand that out to find that 2 to the 5th is 32. So that's the one law that says when multiplying like base numbers, you add the exponents. Well, if we have a law with multiplication, you know darn well that we have the same law or a similar law with division. So if I had b to the m and I was dividing it by b to the nth, or it was written in a fractional notation, we have a law for that as well. Well, let's think about it. If the multiplication turned into addition of exponents, division is going to turn into subtraction of exponents. So this is b to the m minus n. All right, well that seems to kind of make sense, but let's make sure that we thoroughly understand that by expanding one out. What if I had x to the fourth over x squared? I'm now expand it out so that we see the long way, so that we see how the law applies. X to the fourth, once again, would be x times x times x times x. All over x squared is x times x. And now you can reduce. Remember, we can reduce fractions if and only if things are being multiplied. They are factors. And since everything became a multiplication on top, we can cancel anything on top that matches with anything on the bottom. So x on top and an x on the bottom, bing! Remember, anything divided by itself is 1. X on top and the x on the bottom, bing! 1 times 1 is 1, times x, we're left with just x times x, which we call that x squared. How could I have gotten x squared from x to the fourth and an x squared? Subtract the exponents. 4 minus 2 is 2. Oh, that's kind of a fun one. I like that one a lot. Let's do that one again. Let me do another one. What if we had x cubed over x cubed? Whoop, gotta move my paper up. X cubed over x cubed. Well, okay. I'm a smarty pants now, so I can use the law that says, aha, when dividing like bases, when the base numbers are both x, I can subtract the exponents. So I would get x to the 3 minus 3, which is x to the 0. Well, what the heck is x to the 0? I'm stuck. Nope, I can do something else. Okay, forget the law. Forget the law. Let's do it the long way like we did up here. Okay, x to the third is x times x times x. And x to the third is x times x times x. Okay, and then we get to cancel. Ooh, that's the fun part. Anything over itself cancels to a 1, so we go bing, bing. Okay, everything canceled out, and I'm left with 1 times 1 times 1, which is 1. Wait a second. If the law works and the long way works, which they're both legitimate legal ways to do math in math land, I got 2 answers that look different. I got 1 over here and I got x to the 0 over there. What can I say about that? I don't know. Think. Well, x to the 0, isn't that just x? No. X. She just said before that every number has an exponent on it. So if it's not up there, it's a 1. So x is just x to the first. That's not the same thing as x to the 0. X to the 0, it must be 0. That doesn't seem to make sense because exponents is repeated multiplication. If I start with a 0, how do I go anywhere with repeated multiplication? 0 times anything is 0, and I go nowhere. I'm treading water. I'm like Wile E. Coyote trying to go after the Roadrunner, just spinning my wheels. Okay, think. I did it the long way and I came up with the answer of 1. I did it using the law and I came up with x to the 0. Both of them are legal ways, which means that the answers have to be the same. I have to get the same answer either way. Same answer. Oh, that means that x to the 0 has to be the same as 1. So my conclusion is going to be that anything raised to the 0 power is the number 1. Ding, 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 ding. Whoop, whoop. $1 million winner. Yay! We need to generate the repeated multiplication. In order to find out what 2 to the 5th is, we would have to start with the number 1 and go 1 times 2 is 2, and 2 times 2 is 4, and 4 times 2 is 8, and 8 times 2 is 16, and 16 times 2 is 32. To generate multiplication, the identity of multiplication is 1, because 1 times anything is anything, and it starts us off. So if we have a 0 exponent, the entire entity, not the exponent, but the entire entity of b and the power changes to the number 1. Wow, that's fantastic! Alright, so if I had negative 732 raised to the 0 power, because the 0 power is on the outside of my parentheses, everything in the inside is being raised to this 0 power. That means that this whole thing becomes 1. Cool. Rock on. Alright. So that wasn't so bad. That wasn't so bad indeed. Now speak for yourself. I did. Alright. So that was when the top and the bottom had the same. Let's do one more of these, because this is kind of exciting. All the new things that we can learn. So what if I had x squared over x to the 5th? Okay, using my wonderful law that I learned, I thought the law won. It would say to subtract the exponents. So I would say, okay, that's x to the 2 minus 5. So that's going to be x to the negative 3. So I would take x times itself so that there are negative 3 of them. How do I take x times itself so that there are negative 3? All these darn problems. Okay, let's do it the other way instead. X squared is x times x, and x to the 5th is 1, 2, 3, 4, 5. And then we can have fun with canceling. Bing! Bing! Oh, I ran out of things to cancel. And I have x's left over, but they're down here. On top, I have a 1, and on the bottom, x times x times x would be x cubed. So I used the law, and I came up with x to the negative 3. I did the long way, which is still legal, and I come up with 1 over x to the 3rd. Same type of thought process from the last problem. We did the problem 2 different mathematically legal ways, which means that our results would have to be the same. If they look different, they still mean the same thing. So x to the negative 3 is the same thing as 1 over x to a positive 3. So when I have a base with a negative exponent, it means the same thing as 1 over that base to a positive exponent. So instead of multiplying repeatedly, numbers in the bottom are being divided. So it's going to be divided repeatedly. To change the sign, you gotta cross the line. To change the sign of the exponent, you cross the line. So a negative exponent really means that you're dividing, and when you divide, the numbers get smaller. Now I'm going to let you ponder that one for a little bit. We're going to use that idea of negative exponents in scientific notation. We're not going to make them positive, but we need to realize that a negative exponent means that we're dividing, which means that that number is going to get smaller and smaller and smaller. But before we have fun with that, let's take a little break and go do some multiplying. Now we added and subtracted polynomials by adding like terms. That keeps the variables the same and the exponents the same, and we just add or subtract the coefficients. Now we're going to be multiplying polynomials, and that procedure is a little bit different. the first step is still going to be, in this first example, the distributive property that we talked about before. The term in front gets multiplied to every term inside. So we're going to take the 3x times 2x squared. Well, 3 times 2 is 6, so we multiply the coefficients, but then we take x times x squared, and that's that first exponent law that we just talked about in the last segment. When multiplying like base numbers, we add the exponents. So remember, what's the exponent on this x out in front? That all by itself has the god of Mathland with us. So x times x squared is going to give us x cubed. Then we take the 3x and we multiply it to the next term. 3x times a negative 5x, positive times a negative will make it negative. 3 times 5 is 15. X times x, anything times itself, is a square, because it's x to the first times x to the first, and 1 plus 1 is 2. And then continue your distributing and take the 3x to the last term. 3 times 7 is 21, and the x comes along for the ride. You cannot do anything else with that problem as your exponents are not the same. So you're all done at that point. Something to note. Inside the parentheses here, when we had this polynomial, 2x squared minus 5x plus 7, those terms were not like. So when we take that times just a single term out here, you will not get any like terms here, because you're going to be multiplying or changing each term inside by the same factor, which is not going to make them match. Okay. So when multiplying, we multiply the coefficients and add the exponents. Let me write that down. So once again, when we're multiplying polynomials, when you take each term times another term, you multiply the coefficients, the numbers in front of the variables, and add the exponents. In this next problem, we have what we call a binomial. Okay, a single term is called a monomial. 2 terms is called a binomial. 3 terms, like we had up here, is called a trinomial. And beyond that, we all kind of group it into the terms of polynomials. Monomials, binomials, and trinomials are all polynomials. They just have a little bit more specific of a name. Like a square is a rectangle, but we call it a square because it tells us more about that particular shape. So here we have a binomial times a binomial. 2 terms times 2 terms. In the first parentheses, the terms are x and 8. In the second, the terms are x and 5. Now, when multiplying polynomials, the key is that every term in the first set of parentheses gets multiplied to every term in the second. Now, to help you keep track of all of this, there's a mnemonic device. It's called using the FOIL method. FOIL stands for your first terms. So I'm going to multiply the first term of this binomial and the first term of the second binomial and get x times x, which is x squared. The O stands for your outside terms. Okay, the outside terms, which are the ones on the edges, so that's going to be the x and the 5, and that would give us a positive 5x. The I stands for the inside terms. So if the x and the 5 are on the outside, then the inside ones are here. That would be the 8 and the x. They're both positive, so we go plus. We're multiplying them, so plus 8 times x. And then the L stands for your last terms. So if the x's were the first terms, then the last terms of each binomial would be the 8 and the 5. Remember, 5 times an even number will always end in 0. 5 times an odd number will end in 5. So now we multiplied every part using that FOIL method, but now look at the result that you have. Oh, I notice that the OI in FOIL are like terms. I can add a 5x and an 8x. Now I can't combine anything with the x squared, and I can't combine anything with the 40, which is going to happen 98% of the time. So my final result will be x squared plus, now we're going to the rules of adding. An x plus an x is more of just x's. So it's 13x plus 40. Don't change the exponent when adding. Only change the exponents when multiplying. And that trinomial is our end result using the FOIL method. Let's try another one of those. Here I have 4x minus 7 times the 3x plus 8. Using the FOIL method, which once again is just telling us that I'm going to take this 4x and I'm going to distribute it through, and then I'm taking the negative 7 and I'm distributing that through. So you're distributing each of the terms of the first binomial into all of the terms of the second. So 4x times 3x is going to give us 12x squared. Remember, an x times an x is a squarey. Then we do our outside. 4x times 8 is a positive 32x. Make sure that you put your plus sign to separate your terms. Then we do our inside terms. The sign in front of the term goes with the term, so it's a negative 7 and a positive 3x, which would make a negative 21x. And finally, we have our last terms, which is a negative 7 and a positive 8. That makes a negative 56. Once again, the OI and FOIL are like terms, so we can combine those. Nothing's like the first one, so that comes along for the ride, 12x squared. Then I have 32x minus 21x. That's going to give me a positive 11x. And then the minus 56 comes along for the ride. And that's our final answer. Foiling every day. First term, outer, inner, and then last. Can you tell me how to pass this algebra class? The last section of Chapter 10 on polynomials deals with scientific notation. It's not exactly polynomial material, but it does deal with exponents, and so it does relate to the chapter. Scientific notation is a way for scientists to represent really big numbers or itty-bitty numbers. Okay? Scientific notation is always in the form of some number m times 10 to the nth power. Okay, so every single scientific notation number will have this times 10 whatever in it. Now, what can I say about m and n? M is a number that's between 1 and 10. M is always a number between 1 and 10. It does not include 1 and 10. It's a number, well, it includes 1, but it does not include 10. Okay? So it's a number between 1 and 10, not including the 10. So in other words, it has to be one digit, 1 through 9, and then a decimal point. So examples of what the m could look like, it could be 2.4751. That's a number that's between 1 and 10. It could be 6.89024. It could just be the number 8. It could be 7.14. But it's always going to be one single digit and then your decimal point and any other significant digits after that. The n is either going to be positive or negative. If it's positive, it means that we have a really big number. Because remember, we're taking it times 10 to that many, times 10 that many times. So it makes it a big number. If it's negative, as we talked about before, a negative exponent really means that we are dividing. And taking some number and dividing it makes it itty bitty. So if n is a negative, we end up with a small number. Now, what does this all mean? Why does it have to have that times 10 to this stuff? Well, that's because multiplying by 10 just moves your decimal point over. Now let's face it, scientists deal with really large numbers. Think about all the studies of the universe. How far away is the sun? How far away is the next galaxy? All of these as possibilities. You have to keep that in track that, let's face it, when you get to be billions of light years or miles away, what's a few extra 100 or 1,000 here? So that's why we don't necessarily have exact measurements. We also can't find those. But if I had something like 9.45 times 10 to the 8th, okay, that's a scientific notation number. Every time we multiply by a 10, and there's 8 of these, 10 times 10 times 10, etc., it would move your decimal point over, making the number 9.45 larger and larger and larger. So this is the scientific notation number. To write the decimal equivalent to that, we move our decimal point to the right, because every time we multiply by 10, it just moves the decimal point. We move the decimal point to the right 8 times. So right now I have 9.45, so that would be moving it 1, 2, and then we need 6 more, 3, 4, 5, 6, 7, 8. So we move it 2, 3, 4, 5, 6, 7, 8. And so now the decimal point is over there. Because we expanded this, we took the 10 times itself 8 times, which only moves your decimal point. So 9.45 times 10 to the 8th is the same thing as 945 million. So to convert the scientific notation number to the decimal, we move the decimal point n times, and because n was positive, we move it to the right. Okay. If n was negative, we'd move it to the left. So if I had 2.165 times 10 to the -7th, that means that this is an itty-bitty number because I'm dividing by 10. How many 10s am I dividing by? 7 different 10s. Not the number 70. I'm dividing it by 10 times 10 times 10 times 10 times 10 times 10 times 10. Ooh. Okay. So that makes it itty-bitty number. So I still have that the number 2165. So all of those digits don't change. But then I move it over. Now when you're moving it this direction, it's going to be 7 spots, negative, so we're making it smaller, so we're going to move it to the left instead of the right. The first spot moves us in front, and now I have 6 more, so that's how many zeros go in front. 1, 2, 3, 4, 5, 6, and then your decimal point. You can always check that to make sure that you didn't count incorrectly. It was 1, 2, 3, 4, 5, 6, 7 spots. So the decimal point is now in front. So we have 0.0000002165 is what this number represents. So here the exponent was negative, so we move the decimal point to the left. Now remember, this is converting from scientific notation into a decimal number. So from scientific notation to decimal. If it's a positive exponent, we move to the right. If it's a negative exponent, we move to the left. Which means that if we're going from decimal notation to scientific notation, it's going to be the reverse. Let me show you some of those. All right, write the decimal number in scientific notation, and they give us this big number. Okay, right now, in a really large number, where is our decimal point? Oh, well, a really large number, our decimal point is here at the end. I need to move it so that it's between one digit and then your decimal point and then the rest of your digits. So when I read my number from left to right, it's going to have a single number, then the decimal point. So as I'm looking at my number, it's a single number, 8, and then the decimal point. Then I need any significant digits. I need the 2, I need the 0 because there's a non-zero number after that. But now that it's a whole bunch of zeros, we drop that off. Then, because it's scientific notation, I must have times 10. Because in order to move a decimal point, it's because you are multiplying by 10. The exponent never goes on our number here. Okay. And now we get to count. Yay, love to count. Okay. And we go through and we say, okay, my decimal point is over here. I need to move it so it's between the 8 and the 2. How many spots is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more makes 10. Oh, and another one. So that's 11 or 11. It's a big number, so our 11 is positive. So 8.204 times 10 to the 11th is this big number written in scientific notation. So we moved our decimal point from the end to the left. So when we went from decimal to scientific notation, okay, moving your decimal point to the left means positive exponent on the 10. Right. Before, when we moved it to the left, it was in the other direction. When we had a decimal, or when we had scientific notation, we moved to the left when we had a negative. Now it's reverse. Let's do another one. What if I had this tiny number, 0.000063? Now in Science City, the big city that Mathland is a suburb of, they oftentimes use the 0 in front so that they clearly see it all. We in Mathland, we don't necessarily feel like we need to have that 0 in there. We know that the decimal point means that there's a 0 in front of it. Do whatever you're more comfortable with and whatever you see. Okay. So we need to move this, once again, the decimal point, so that I have one digit and then my decimal point. So that digit is going to be the 6, then the decimal point, and then the 3, because that's another significant digit since it's not a 0. We have to have times 10 to the, because this is writing it in scientific notation. And now we count. We moved 1, 2, 3, 4, 5, But the number 0.000063 is an itty bitty number, which means that our exponent will be negative to make it smaller. Okay. So when we're going from decimal to scientific notation, and we move the decimal point right, means we have a negative exponent. And remember, the exponent is only on the number 10. All right. So to convert from decimal to scientific notation, if you move your decimal point to the left, you have a positive exponent. If you move your decimal point to the right, it means you have a negative exponent. And once again, it's reverse if you're going in reverse. And that's what I have to say about scientific notation. Have a good week, and don't forget to study hard for your final.